Alright, so in this video I'm going to be explaining another important article with the title Moderately Distributional Exploration of Domain Generalization. So our target is not fixed, it is unseen during training. This paper in 2023. To address this issue, we propose to perform moderately distributional exploration for domain generalization. Specifically, mode performs distribution exploration in an uncertainty subset that shares the same semantic factors with the training domains. We show that mode can endow models with provable generalization performance on unknown target domains. So the domain generalization aims to tackle distribution shift between training domains and unknown target domains. Generating new domains is one of the most effective approaches, yet its performance gain depends on the distribution discrepancy between the generated and the target domains. Distributionally robust optimization is promising to tackle distribution discrepancy by exploring domains in an uncertainty set. However, the uncertainty set may be overwhelmingly large, leading to low confidence prediction in domain generalization. It is because a large uncertainty set could introduce domain containing semantically different factors from training domains. So the left shows the causal relationship of data X labeled Y. We have semantic factor C and non-semantic factor S. And the right shows that data X are generated by causal mechanism G, with two causes, your semantic factor and non-semantic factor S. So, given sets of samples called the training data, the aim is to train a classifier F by using the training data. So we have this causal assumption. There exists a causal mechanism such that X of sub t is G of, these are random variables over the non-semantic factor S, and C is the random variable, this one is the random variable defined over the semantic factor C. So this equation means that the feature randoms X share the same semantic C, but don't share the non-semantic factors S. These terms shouldn't confuse you, because in some texts, in some papers, they call it, they decouple their feature vector. They say some of them are domain invariant features, some of them are domain specific features. Now they are saying causal and some other things, but they shouldn't confuse. So there exists this causal mechanism. But here we have uncertainty set and non-semantic space. To enhance the diversity of training domains and preserve the semantics among domains, the uncertainty set where we perform is defined in the following. And A here is a parametric space. Psi is a function that could generate random variables. This omega is the set of random variables defined over S. The non-semantic space is defined in the following. And D is the distribution with respect to random variables S above. So we introduce some necessary concepts about risks and models. So denote F sub W by the model depending on the parameters, where W is the parameter space. Given a loss L with respect to training domain, the training domain risk, the model is this, and the corresponding empirical risk with respect to F is this loss, the average of loss. So it's empirical risk. Lastly, the target domain risk. But we don't know the real distribution. So this is the realistic, but we need an empirical measure. We cannot do this. We need some empirical like this. So we introduce our main motivation to generalize well on the unknown domain. It is one of the most effective strategies to generate new domains to enhance performance of deep neural networks. But this research area, distributionally robust optimization, is a possible strategy to tackle distribution discrepancy. This is because it extends one distribution to a distribution space, the uncertainty set, and trains the models with the worst case distribution in uncertainty set. By ensuring uniformly well performance inside the uncertainty set around training domains, distributionally robust optimization can enlarge the influence of training domains and thus shrink the distribution discrepancy between the test domain, training, and test domains. But in this paper, the innovation is that they are using this one, the moderately version of distributional robustness. So the considered uncertainty subset is used for exploiting the worst case distribution, performing it on subset of non-semantic factor, which can be captured like this. It's a mean max of expectation. So it is challenging to exactly estimate the distribution under domain generalization scenarios, resulting in restricted searching capacity. Therefore, we propose to explore the non-semantic factor for each sample rather than for each domain. So again, min is over W, but we are using expectation of max of loss for each S in S sub omega, because S sub omega is a non-semantic space. The corresponding empirical risk now can be calculated. And C sub L here is the element of the semantic part of G inverse. And then we further introduce the empirical risk, namely both the exploited and original data are used for model training with a parameter beta for a trading of their risks. So optimal transport between two probability distances, because it's expectation of your cost function to go from one distribution to the other. So we'll skip this. This theorem says that assume that your loss is bounded and your S sub S1, S sub L are mutually independent. Let W hat be solution of 11. 11 is here. If we have found the solution of this optimization problem, then with probability at least this one, the risk minus minimum of risk is upper bounded by this epsilon, which is equal to this There is another theorem that says, given the same condition in the theorem that we discussed, and let W hat be a solution. If the cost function is continuous metric and L is LC Lipschitz with respect to, for example, this one, and by the way, in mathematics, we call this Lipschitz constant. Then with probability at least this, it is upper bound now with this variables. So you see the visualization results of normal exploration process where semantic information is preserved when exploring non-semantic factors. And here is the Fourier-based algorithm. The top left is the input picture and the rest are amplitude provider. In an iteration, the controlling parameter alpha are used to mix the amplitudes to obtain a new amplitude together with the phase of the original input image to generate the augmented image. These Fourier transforms are very important. For example, in convolutional neural networks, we can also use wavelet transform. And of course, there are some papers that don't even learn the weights. Because, in convolutional, we learn the weights of the kernel. But in some papers, they just fix it and they just accept whatever it is. Because they say that in your brain, you are not learning the weights of your kernel. So it is just fixed, especially near your ear. If it is your head, near your ear, the neurons are just receptors, and they don't train every time they receive a signal from outside. And here is the other in-based approach. The top left is input containing image, and the rest are the style provider. We give it to all encoders. We have feature map for each of them, and then we can get the mean and standard deviation. Then we mix their standard deviation. Then we give it to decoder, and we can calculate loss, then backpropagate. But the overall approach is like this: using existing generation methods like style trans. This model, the model of this paper, could create more aggressive samples by updating the controlling parameters alpha. So you can have a sequence of images.